Now we want to apply our theorem to an example. We look at the binary symmetric source and Hamming distortion. So we have the binary symmetric source, Px. It produces 0 and 1 with probability 1/2. And we suppose Y is an output of a binary symmetric channel that has input X and crossover probability P. That means if the source outputs 0, then with probability 1 minus P, Y is also 0. We use two encoding strategies and time share between them. So let's look at the first strategy. In the first strategy, we choose U as the output of the binary symmetric channel with input X and crossover probability beta. So we create a codebook in this way. So of course it's the same. If X is equal 0, then we have the probability this U is equal 0 is equal 1 minus beta. And if X is equal 1, then the probability that U is equal 1 is 1 minus beta. So further, we choose as estimate of X hat just U. So in this case, somehow we just don't look at Y. So and then we compute the mutual information between X and U minus the mutual information between Y and U. The mutual information between X and U is the entropy of X, which is 1, minus the entropy of X under the condition U. But if I know U, then the probabilities of X that it is 0 is beta and 1 minus beta. So we have here the binary entropy of beta minus the mutual information of Y and U. So that's the entropy of Y is again 1. And here we have the entropy of Y if I know U. And then we you can look here. Then this is equal, the probability is equal P star times beta. So because I know U, then here this is the probability that X is equal 1 times P, and here X is equal 0 times 1 minus P. And so that's the probability distribution for Y under the condition U, and therefore we get here the binary entropy of P star beta. So we can write this as the binary entropy of P star beta minus the binary entropy of beta. And the distortion, the expected distortion of X and X hat is equal to beta because we choose X hat equal U. Now look at the second strategy. So in this case, we do it the other way around. We choose U equal 0. That means we ignore just this output of the codebook, and we just use the site information. So our estimate is just equal to Y. But of course, if we now look at the mutual information between X and U, that's 0, of course, because U is just 0, and the mutual information between Y and U is also 0. So we have here 0. But in this case, of course, the expected distortion is equal P because Y is just an output of the binary symmetric channel of X. Now the idea is that we use a fraction lambda for the first strategy and a fraction 1 minus lambda for the second strategy. That means if we have block length n, then we have n times lambda, the first strategy, and n times 1 minus lambda, the second strategy. Then we can achieve this rate here. Because here we have for 1 minus lambda, we have a 0, and for lambda, we have this here. So we can achieve this rate, and yes, and if you have a look at this and compare it with the rate without site information, we know from the previous section that this is 1 minus the binary entropy of D. Then we will see that this compression is better So one can check that this y rate is larger than 106 unless d is equal 1 over 2, p is equal 1 over 2, unless r of d is equal 0, or x and y are independent. Then we can consider the case if the encoder also see y. We analyze this in general and just can put it into the formula and then get this rate function here. We get here not the lambda disappeared, we just get the h of 2 of p minus h of 2 of d. And we find that this rate is less than 106 unless d is equal 0, p is lesser equal d, or p is equal 1 over 2.